morning. My name is Tolga. I'm guessing me right? So just the one slide sort of about Onica, the company that I work for. Onica is an Amazon Premier Partner. I promise my IBM friends we won't get in a fight this morning. We pretty much everything related to AWS. IoT being one of our specializations, software development in a cloud-native way being another, migrations, big data. There's some hints here on the kinds of projects we've worked on. We're based in California with offices in Dallas, Chicago, and expanding now into the East Coast as well. I'm a software engineer by trade, so I'm going to talk about a lot of hardware stuff today, but I'm faking it. I became CTO of Onica by way of acquisition, so I had a premier partner that I was a co-founder of that got acquired by Onica last year. And my role now is to oversee the technology strategy of Onica as a whole. So we're going to talk today about IoT detached from technology at first. So just kind of remove any specific tech and just talk about the business of IoT. We're going to go into a couple of AWS specific approaches to IoT. And then at the end, I'm going to share with you a case study from one of our customers. All right, so first though, let's just detach from the specifics of any particular platform or tool or use case and just look at IoT a little more broadly. Okay, to start that conversation, let's make sure we all think of IoT as the same definition. So I think of it as pretty much any device that's lower power than your cell phone from a compute power point of view that's connected to the internet. Now, that doesn't mean it's small. There's huge industrial devices that are connected to the internet. There's teeny little sensors that we see, plastic sensors somebody was showing, that's cool. Oh, that's you. Yeah, and so I think people's minds, and probably not this group's mind, but if you walk out on the street, people's minds really gravitate towards a couple of common use cases like home automation and office automation. But we want to make sure we're thinking more broadly than that. Lots of industrial use cases in this space, lots of healthcare use cases in this space. So just very broadly. But it's not a specific technology, so we see a lot of confusion about this, and it doesn't help that there are products that are named IoT that add to this confusion. But IoT is a concept, not a specific tool. You can't reach into your tool bag and pull out the IoT tool. And then when we look at IoT applications, we sort of see a common pattern emerge, and this is that pattern. So we've developed this understanding of an IoT application after doing it a bunch of times and trying to sort of decompose, man, what is it we're doing every time, into the simplest diagram. So if you look at this diagram for a second, on the far left is your device, right? That's probably the most tangible part of an IoT project, right? The thing you hold, touch, feel. Then there's some kind of ingestion component, which is typically focused around security and safely collecting data and not losing data and being able to scale up to the data volume that you need. Then there's the sort of two different processing workflows we need to examine. There's the top one there, which is the reactive workflow. So the reactive workflow would be, hey, you left the freezer door open and the freezer temperature is rising and you want to notify somebody that they should close the freezer door. That's that sort of immediate real-time reaction. It doesn't do us any good to analyze that tomorrow because the food's already spoiled. That's the stuff we need right now. The second flow here, though, is storing and analyzing the data over trends. So if we're looking at the temperature over time and we want to do something interesting with temperature over time, that's that second sort of flow. And it's different because you don't use the same tools or technology for these two workflows. And then finally, there's always some API, almost always some API that's exposed to a web or mobile application of some kind. And so we can't forget about, hey, okay, we've stored this data or we've reacted to this data, but typically we want to do something more than that. We want to actually, I think probably 80% of IoT devices today have a mobile app somewhere. Okay, so then we look at these use cases. We've bucketed into three categories all of the IoT use cases that we've seen. Now, I'm sure somebody here will find a use case that doesn't cleanly fit into one, but hopefully it at least kind of fits into one of these use cases. Let me just talk them through. The top use case, that top category, is when the purpose of the IoT product is to be an IoT product. And I know that sounds counterintuitive, but like a connected light switch, its existence is because it's a connected light switch. Like, that's why it exists. So they're direct end user value. It was built to connect sprinklers. Anything in the sort of home office automation space fits into that first category. The second category is still customer-centric, still end-user value, but focused around reliability, focused around warranty service or service plans or white glove service to say, hey, this hardware is going to fail soon. We see patterns of this failure. We're going to ship out a replacement part. Or we're going to do some performance metrics on this big industrial device and tell you more about how it's performing in your environment. But still sort of focused on the end user. And then the third one is actually an inward-looking use case where it's not really focused on your customer, but it's focused on your engineering team. How do we make this thing more reliable in the aggregate? So not why did this one machine fail, but what makes the machines fail in general, and how do we learn from that and engineer better devices? So we see customers usually start IoT adoption in one of these three and then oftentimes expand into the other two as well. A lot of devices fit all three categories. So, is your hand up?
No, sorry. I was resting. Good observation.
Okay, so then as we talk to customers about IoT just about every day, what are the things that are preventing or that are business considerations beyond the tech, right? So we're primarily a technology consulting company. We help customers work through the tech, but at the same time, we have found that these questions have to be answered for our customers to succeed in their IoT projects. So for example, take the business model questions. If you are a widget manufacturer, you make widgets and you sell widgets. Your business model is, hey, we have a cost to build the widget, we have a cost to distribute and sell the widget, and then we're kind of done. We might have a warranty or something, but for the most part, we're not incurring any more cost after we've sold that widget. Well, if that widget is IoT connected, you probably are incurring some cost on a go-forward basis. And so how does that fit your business model? The best fit, or the easiest fit, is if it's a disposable device. So if you have a wearable, most wearables are just designed to only last a few years, and so they just build the cost of that ongoing infrastructure and expense into the wearable's purchase price. That's a great kind of customer experience. But if you're making an industrial device that lasts 20 years, that's probably not practical. So then you have to think about how do you monetize and cover the cost of this ongoing infrastructure and services and teams that have to monitor and maintain these cloud-side systems. You also have to figure out how you're going to staff up to deploy the actual infrastructure. So a lot of companies that make widgets, what they don't do very well is operate cloud environments. And so this is a net new skill set that has to be introduced into those organizations. A lot of times, distinct from the IT sort of role, these are product engineering roles that are getting involved in deploying the cloud. And then you have to worry about how do you provide worldwide coverage for your support and infrastructure. So a primarily US-based operation may only be open during the day. You've got employees today that only work US daylight hours. But now you've got your devices that rely on your infrastructure 24/7. So now all of a sudden you have to have service and network operations type folks available in the middle of the night. That second to last bullet is aggravating to me. The privacy laws have gotten very complicated. You guys may know GDPR is launching here. It's like right around the corner. But beyond that, there's laws in Canada, there's laws in China, there's laws in almost every country now developing over this privacy issue. And almost certainly some laws coming our way in the US as well, if I was a betting man.
Well, the good news is that Facebook and Cambridge Analytica helped us out a lot.
That's right, yeah. That was super helpful to this problem.
Super helpful.
So, these privacy laws unfortunately require you to think and engineer in a way that meets the law's intent and the law's letter, while not crippling your application. This can get really challenging with data locality, requirements to encrypt or not encrypt in some countries, which is amazing. So this is a challenging space. And then the last one is about connectivity, and I kind of mean, in this case, cell connectivity. I'm going to talk about it in the next slide. So, if those are the business barriers, what are the technical barriers? The technical barriers are 2 slides worth. The first one is security. The security thing is a really, really big deal for IoT devices. You guys all remember the the major retailer that was hacked a couple years ago.
In Minneapolis?
Yeah, those are the guys.
Okay.
You know, it was kind of a big deal, and it was an IoT device that enabled that attack to occur. It was an unsecured, vendor-managed IoT device. That's incredible, and it's really elevating the risk profile of IoT devices. And so, since then, there's been a dozen more of these things. There were the DVD players that were attacked and used as a DDoS against the DNS infrastructure. I think it was last year, maybe 18 months ago. This is a continual problem, and it's not just the security of your data and your customers, but it's your device being turned into an attack vector against others as well. Then the next technical challenge is connectivity. With connectivity, it ranges from super simple to super hard. So if your device is powered from the wall, like wall powered, and you have Wi-Fi, then this is a really easy problem, use Wi-Fi. As soon as those two things aren't true, which is like 85% of the time, then you're going to have some kind of connectivity consideration to make. Who is doing LoRa? LoRa? That's me. Yeah, LoRa. So that's cool. Those kind of things are enabling applications that are lower battery power. And of course, building out your own LoRa network is painful, so having one you can use is great.
By the way, you can call me and we'll hook you up.
Yeah, you heard it here first. So, LoRa, and there's Sigfox, there's LTE category M, which I think is going to be really, really big for this space.
There's waitlist and there's RPMA as well.
Yeah, so there's a bunch, and someone's gonna win, or there's gonna be one or two winners out of the bunch of technologies that are involved. The name of the game is low power connectivity, right? And that really ties into my next point about battery. So if we think about battery technology today, it is the thing holding back the rest of technology. Not just IoT, but everything from cars to cell phones to laptops to IoT devices. The constraint almost always is battery. And of course, if you had unlimited size and money, maybe you could always get a battery large enough. But most of these IoT devices that we're talking about, we want them to be small, and that doesn't play real nice into the battery problem. So imagine a device that's both small and battery powered and cell connected. You're just not going to get. I mean, look, Apple tries really hard, but your cell phone still only lasts one day. So. Okay, then there's the sensor part. The sensor part of this is actually the easiest part. So there are a lot of people making a lot of sensors, and maybe the hard part of sensors is picking the right one. There's so many options. But you're probably not going to go engineer your own sensor, which is great, because that would be quite the R&D project. But this next one down, integration. So we have customers come to us and say, all right, so I've got this form factor. I want to use this battery. I need this sensor. I want this connectivity. Can I buy that off the shelf? Like, well, no, not really. Like the permutations of just multiply those out. These things don't exist off the shelf. What you end up doing is buying the components and integrating the right solution for yourself. And some customers are really, really scared of that language. And I want to tell those customers that it's not scary. We're not talking about major R&D projects. We're talking about pretty straightforward integration of well-understood components. We do this integration work as a big part of our practice, where we put together the right set of components for people, design the right PCB, build the right firmware, and we do it in weeks, like 3 weeks, 4 weeks, not months or years. The next one is about scale. Scaling for IoT devices, I think, comes in two flavors. There's scaling your data ingest part. Can I keep up with the data flow that's coming in? That's a compute-related scaling. And then there's how much data am I storing, which is primarily a disk space issue, but it can also be a compute issue. If you store a lot of data, it costs more to compute across that data when you want to get some answer from it. So while it sometimes seems smart to store 15 years of your IoT device data, just realize that means every time you want to go look through all that data, it's going to take more time and more compute resources. And the last one about updates kind of ties back to the first one about security. If you can't update your device in the field, then your device could become the next sort of attack vector. And if that's going to be embarrassing when that happens, it's going to be even more embarrassing if you can't update it to make it stop. Okay. So in AWS, this is actually an old chart. There's maybe a dozen more services since this came out. But the point here is the breadth of the platform. So when we look at AWS and we look at IoT, there is a service called AWS IoT. It's actually now called Iot Core. But it's not the whole IoT platform. So AWS IoT is focused on an ingest problem that I talked about. And all these other services solve for the other parts of that diagram. So I put the slide up just to kind of orient people around the idea that you're not just going to be using one AWS service for your IoT app. You're going to be using a whole bunch of pieces of the platform. And that's where integrators like us can come in and help you navigate the options. Okay, how are we doing on time? Good.
45 minutes.
All right. Yeah, I'm going fast because there's a lot of slides here. So now let's talk about ingest with AWS IoT. So now we are shifting focus from IoT generically to specifically AWS IoT. And specifically this ingest part. So the service that you see on the screen here, the yellow boundary, that's the service that we call Iot Core. So if you look at the AWS marketing materials, and you hear them talk about a service called Iot Core, it's what's inside the orange, I guess, boundary. On the left side there's an SDK that enables your device to connect to the service. It's really just a wrapper around MQTT, but it does provide some high-level APIs that are really nice. But if your device couldn't use the SDK, you could just use MQTT directly. Then that SDK connects to the device gateway here in the middle. The device gateway is the workhorse of the AWS IoT platform. Its job is to route messages to where they go. So you'll see I've got two paths up there. It can route to the rules engine or through the rules engine into other parts of the platform, or it can go to the device shadow service, which I'm going to talk about in a second. While it does that, though, it also takes care of the security, authentication, and authorization pieces of the problem. So making sure that your device is the device you think it is, making sure it hasn't been cloned. These are the kind of problems you can solve with good discipline by using the service. Okay, so let's just look at a possible IoT message. This one's a JSON formatted message, which works really well for AWS IoT. This is a turbine that's publishing some temperature, frequency type data. It could be a wind turbine, it could be a pump, it could be a jet engine, doesn't matter, it's some kind of turbine. And this is your typical sort of fire and forget message flow. So I've got a sensor, it's reading some values, and every second, or every tenth of a second, or every 2 minutes, whatever the right use case is, we're going to submit this packet. And we probably, as a device, don't care much beyond this. But what if we did care? What if we wanted to control the device? So let's move away from turbines, because I don't actually recommend controlling turbines from the internet, especially not ones that are on jet engines. But if you look at something a little more tangible, like a sprinkler, take a lawn sprinkler. So a lawn sprinkler that you can turn on to water your lawn, turn off to not flood your lawn. It connects to the service, it subscribes, it says, hey, I'm sprinkler 456, and I'd like to know when you've got messages for me. And your control logic, which is probably a mobile app, right? Because if you're going to buy a connected sprinkler, again, you're probably buying it because it has a mobile app. So your mobile app, supported by some cloud-side APIs, is saying, hey, let's turn the water on. We're ready to water the lawn. And the device gateway faithfully delivers that message, and everything is great, we're watering our lawn. Except that doesn't work. It doesn't work because what if you take your phone and you say, turn the lawn sprinkler on, and you realize you made a mistake, you accidentally hit the button, and you immediately say, turn it off, within a split second, turn on and off. Well, nothing guarantees that those messages will be delivered in order throughout this whole kind of system. And so what if they're not delivered in order? What if I say on then off, but what's received is off then on? So let's play that out. The sprinkler gets the off message and goes, cool, I'm already off, thanks for that. And then it gets the on message and starts watering your lawn. Meanwhile, your application thinks that it's off. Like you've got completely the wrong state, your lawn is flooding, and your neighbors are mad. So how do we avoid this problem? We could go build a bunch of sort of versioning, timestamping stuff in our own way between these devices, or we could use that device shadow service I talked about. So the device shadow service solves that exact complexity for you. It's not magic, it's still just built on that same messaging workflow you saw earlier, but with using the SDK on the device side and the service on the cloud side, you avoid all the complexity of getting the versioning and timestamping right. It looks like this. So here we've got a device that's got a color selection and an engine on-off selection. So the color is red and the engine is on, or that's what we want rather. But what's true is the color is green and the engine is on. So the difference there, the delta if you will, is the color should be red, right? We're not the right color at the moment. If you're a device-side firmware guy, this is all you have to pay attention to. Is what's the delta between the state I reported and the state that was requested? And you try to make the current state match the desired state. But there's a number of reasons that they may not match. The device could be offline, so maybe we changed the color to red recently and the device hasn't picked that up yet. It could be offline, there could be a connectivity issue, its battery could be dead. It'll come on eventually and pick up that message. Or the device could be unable to go into the state we asked for. Maybe there's some reason it can't do it. So having the two concepts of like, what did I ask you to do and what are you actually doing, really simplifies the development problem for both the application developers and the embedded developers. Okay, so that's the device shadow. If you remember earlier, I talked about the rules engine that can route messages to a bunch of AWS services. So here we have 5 of those services. There are more than 5 that integrate, but these 5 are interesting and probably used in every application. The first one is actually not really specific to IoT. It's API Gateway. API Gateway is how we expose APIs to web and mobile applications when we're building serverless applications in AWS. And so it fits into the picture here at the top. So this is the IoT service we're talking about. It's talking to our device. This middle area is whatever our application is. Our application can be using Lambda, which I'll talk more about. It can be running on an instance on EC2. It can be running on a data center somewhere. Doesn't really matter. What API Gateway does is gives us kind of a place to do security and auditing and routing of our API messages. And I put that in here just because I think, again, every IoT application has this element of exposing data via an API. So then let's look at Cognito. Cognito is an authentication service that helps you build kind of registration, forgot password, and login workflows. And it's a very underappreciated problem. I think every mobile sort of app developer at one point has had to build a login flow, and they've always probably trivialized that. Like, oh cool, username form, password form, it's easy, right? And it sure is until you get to like multi-factor authentication and integration with ID providers and forgot password workflows and registration workflows and phone number validation and email. I mean, it actually turns out it balloons into quite the problem space. Cognito does this for us and integrates with a lot of services, but most significantly with API Gateway. And so in this case, our mobile app can obtain credentials through Cognito and then use those credentials to call our API. And Cognito will take care of registering, verifying, forgetting passwords, all that stuff. Okay, now let's talk about Lambda. So Lambda is a more obvious integration. Lambda is the serverless compute workhorse of AWS. So this is where you can run code without running servers. And so in IoT applications, it's very, very handy to be able to react to events in this way and not have to manage a fleet of servers or scale them. We're going to dive deep on Lambda here in a few slides, but for now, let's just say there are these 4 platforms, and actually Go was added recently as well, that you can write code in, give that to Lambda, and Lambda will execute that code in response to some event. That event could be an IoT event, as it's diagrammed here at the bottom. We're going to talk now about Kinesis, and Kinesis is another service that's perhaps a bit misunderstood. It does a bunch of different things. I'm going to show you 3 use cases for it on the slide. The top use case is actually super handy. It lets us take our IoT messages and use a product called Firehose, it's part of the Kinesis family, and store that data in S3. So S3 being the storage workhorse of the ecosystem, if we can take data that's coming in through the IoT service and store it in S3 and never have to use any compute capacity of our own, we spare ourselves from any work on the ingest pipeline at all. Data just lands in S3, and then we can use whatever big data tool we want to use to go do that kind of analytical workflow. It's not going to work for that real-time workflow. It's not going to be the place you notify someone that the freezer door is open. But it's the place you're going to do temperature over time, or attendance over time, or whatever the thing you're trying to track is. The middle workflow, notice I put it between Lambda and Kinesis. One slide back, I had IoT going directly to Lambda, and now I put Kinesis in the middle. When you put Kinesis in the middle of that workflow, you get a nice little buffer. So if something is wrong with your application that's not working, it's returning errors, without Kinesis in there, those messages would get dropped. With Kinesis in there, we get a buffer of up to 7 days, but those messages will persist, so that we can repair the application and not lose messages. For some applications, losing messages is fine. So if you're measuring temperature every second, of like ambient temperature outside, who cares if you lose one? Like you're gonna catch up 1 second later. But if you're doing something more critical and you can't lose a message, then having a buffer in the middle is super helpful. And the bottom use case is for when Kinesis or when data rates are really high. So the IoT service can handle really high data rates to a point, but if we're talking millions of data points per second, like you've instrumented a spacecraft or something like that, Kinesis is actually a data source that can absorb data at a faster rate and scale more cost effectively for really high data rates. But it's not as flexible as the IoT service. It can't do message routing, it can't do the shadows, it's one way. So in those use cases, we often will connect to IoT for command and control type communication, and Kinesis for the really fast data rate. But don't prematurely do this. You'd have to have a really, really high data rate for this to make sense.
I have a quick question.
Yeah.
In the previous slide, before this one, you have the AWS Lambda and AWS IoT in different parts of the chain. In one case, it goes through Lambda, and then it goes to AWS IoT. Did I read that right? Or?
Yeah, so here, we're using Lambda for two different things. We're using Lambda to service API requests from our mobile clients,
okay.
And we're using Lambda to service incoming messages from our IoT device. And then here,
What's the use? Yeah.
we're still doing that in this middle flow, right? We just put this buffer in between. I'm just not showing the API part in this diagram.
Okay.
Right?
But here, this is a different instance of the Lambda, the AWS Lambda here, or is it the same?
I mean, Lambda is a service, so you could call the Lambda directly. You can call the Lambda through Kinesis. It's the same product.
Okay.
Yeah.
We just don't maintain the server platform, right?
Right. I'm going to talk deep about Lambda in a second, so you'll get a good feel for that. And the last one is Dynamo Db. So Dynamo Db is a NoSQL database, which means you have to pivot the way you think about databases. You can't apply sort of typical database concepts to it. It's very fast and it's very predictable, which is in fact the more important attribute. So when we say predictable, what we mean is whether you have 1 record or 1,000,000 records, we expect to see about the same performance results. And that's a really desirable property when you're building IoT apps, because IoT apps tend to have scale, massive scale. It's very cost effective. So it fits in the architecture here. Typically, if you're using Lambda as serverless compute, then you're going to want a serverless database as well. DynamoDB is a nice serverless database. The one thing about DynamoDB is it's not really a great time series data store, and a lot of IoT data is time series. Like at this time, the temperature was this.
Well, especially if you want to do predictive.
Right, predictive stuff, exactly. Or any kind of analysis of the past. And so we use DynamoDB to store the current state of the world, but we don't usually put the historical data in DynamoDB. And in fact, I'll show you now how it all fits together. It's a little bit hard to see. If you take all those concepts, though, kind of put them together. On the left side is an IoT device, talking to the device broker through the rules engine. And then there's 2 flows. Notice the forking there at the rules engine. The top flow goes through that Firehose product and stores our historical data in S3. So these are actually just being stored as files. They're not in the database at all, and they're not indexed at all. Because in the modern day approach to data engineering, we'd actually rather just analyze the data with some kind of big data tool, rather than sort of pre-index it most of the time. And then the lower flow has a Kinesis stream as a buffer, routing to our Lambdas. Our Lambdas are also servicing API gateway. So we've got a web-based API that's being used by mobile apps or web apps. And then we've got Dynamo Db here for that sort of active, working, real-time, current state type information, but not the time series. These are notification services, so push notifications or email. And then this is hosting our actual web application. So that's like the whole thing put together, and we think this diagram is pretty much where we start every IoT project with today. And we just figure out what needs to be customized for each customer.
Do you see clients using RDS for relational database for the time series and predictive stuff?
Sometimes, yeah. I mean, sometimes you can. You definitely can. The problem is any database, eventually, the time series stuff is really hard to do well in databases, in traditional databases, because at some point, like the index, so you're gonna have an index on date and time. The index is gonna get really, really big. It's a lot of records, and so it's doable, and we've seen it done, and we've done it. But in the modern day approach, I think I'd rather put the data in S3 or an object store of some kind, and then use any sort of Hadoop and Friends tooling that we feel like using, whether it's Spark or just basic MapReduce or Hive or Presto. It doesn't really matter. We'd probably prefer to use one of those tools to analyze the data and then run batch jobs over it. So analyze it every hour if you need to, and reduce it from, because you don't really want all the raw data points anyway. You usually want some insight instead. So reduce the data into whatever's insightful and store that insightful data in Dynamo or RDS or something.
Don't people normally though when they're doing series data, store the exceptions and not the data, the data? So if there are exceptions where it doesn't go, you assume that the data string is correct, and if there was an exception, that's what you store?
So I think that would have been an approach that we would have thought about a little while ago, where, hey, look, just store when things are out of the norm. But if you want to do AI later, some ML later, you really want a large set of correct data as well. And so having the correct data is almost as important as having the incorrect data to be able to train AI ML models. And the other thing is you don't know what some analyst 2 years from now is going to want to glean from that data. And so you're making a lot of assumptions about what's normal early in the design, as opposed to just storing it and then giving some options to people down the line to make some choices.
If you wanted to see a real-time, like a Datadog graphical display of the past X hours or 7 days, does that fit in here, or?
It's definitely, so kind of. It depends on your data rate. Let's say you're sending samples 10 times a second, but you want to see an hour's graph. Well, you probably don't need to see every sample. You want to see like 1 minute reductions of those data points, right? So you can do the 1 minute reductions of those from the data in S3 and then store the sort of cooked data somewhere else.
So that's another process pulling it out of S3.
Yeah, you have some job that's running that's reducing the thousands of data points into the 60 you care about. And that 60 you can store anywhere. It becomes easy at that point. Now, if your data rate is slow, then maybe you don't need to do that. But I just assume for this conversation you've got a high data rate. And of course, there's other solutions here. Another one that we do see used, not RDS, but Elasticsearch. Elasticsearch is actually a decent time series data store. As you guys probably know, it's used for log data a lot, and log data is essentially time series data, right? Time, events. And so Elasticsearch is not a bad option. I wish we had sort of a true serverless product in the space that did good time series data. We just don't have it today. Okay. All right, good. So I want to talk now, this is a related topic to IoT, but not specifically about IoT. Let's talk about serverless computing. So when we say serverless computing, we mean writing code and having the platform run it for us somewhere, without sort of caring about where, for the most part. Typically, because if you don't care where your code runs, then things like high availability become really easy, because if the server that was running on dies, and it runs on another one, what's it to you? You don't know where it's running anyway. So HA, DR, these things have become a lot easier. Scaling becomes super simple. So in general, when we're building serverless apps, we're looking for services that we can manage as opposed to servers we can manage. The goal is to end up in a state where we don't care about these things. We don't care about OSs. We don't care about containers or container management platforms. We don't care about any software except our code. That's the nirvana of this approach. And we want to scale kind of differently too in a serverless application. So this is a really interesting problem space. Today, if you guys have done work with application teams and launched a big sort of, let's say, web-based application, there was a conversation at some point during the dev cycle that was like, hey, how many servers do we need? And how much CPU power and memory do we need? And here, maybe you didn't know that this would happen, but what the guy you were talking to did is he made up a number in his head, and he doubled it, and that's the number he said. Because there isn't a better way. There isn't a scientific way to say, well, we have 10,000 users per day. How many servers is that? 4? And it's because a 3 gigahertz CPU today isn't the same performance as one from 2 years ago, even though they're the same speed. Furthermore, depending on your application, we don't know if it's better to put a lot more power on one instance or to put some smaller power instances and have more of them. Right? That profile is different for every single application in the traditional world. And so you're actually solving two problems at once. You're solving how much resources one request, one user needs, and then how many resources do all my users need. It's not a simple multiplication problem because depending on your application code, it may not scale linearly like that. Well, what if we could only focus on one problem, which is how much resource does one request need, and then let the platform worry about the second problem. So this is where serverless computing is really, really interesting because you only have to plan for a single request at a time. So the service we're going to dive into in a second, which is called Lambda, will take care of running additional containers for you without you having to worry about how that works. So if you know that this is enough resource to do one request, if you have 10,000 requests, then there'll be 10,000 copies of your code running in 10,000 different places. None of them sharing any resources at all. It's a different way of thinking, and it does require you to change how you develop applications because it's completely stateless. There's no, if you have 10,000 users, they are all running 10,000 different copies, and you don't even know where those other copies are. But if you embrace that stateless sort of programming mentality, you're able to focus on just what it takes to solve the business problem and let the infrastructure take care of scaling that out. So that's scaling. The next part is about cost. So in even the most optimized applications that are auto-scaling, that are doing all the right cloudy things, there is inherently some idle capacity. It's really, you can't ride the threshold so close, right? Where there's nothing wasted. But in serverless apps, there's actually nothing wasted because if there's no active event being processed, there's no code running, you're not paying for anything. So the specific service I'm kind of leading up to is called Lambda. It's function as a code, or function as a service. You write in Python, Node, Java, C#, or Go. And once your function is running, it can do everything. It feels like regular code running in a regular runtime. You can make network requests, you can use other services, you can write to temporary disk, all the stuff you would do with your code. But your code only runs for the duration of one request. When that request is over, that code is no longer running until the next request comes in. And again, as I said earlier, your code could be running in 5 places at once as well, servicing 5 different requests at the same time. The way you deploy Lambda is by packaging up your code and resources and libraries into a zip file, and putting that zip file in S3, and then you wire up the right events to trigger your Lambda for the right condition. To invoke Lambda, here are some of the services, there's actually more, that can invoke Lambda. But the ones that are most interesting for our conversation today are API Gateway, because that's how we're going to take care of web requests, and AWS IoT, because we're going to respond to IoT data. So with those two integrations with Lambda, you can make a completely serverless application. The lifecycle of Lambda looks like this. So a request comes in, a new container is created, and in this case, when I say container, you you can imagine Docker-ish something. It's not actually Docker, but a container is created. You're given a sandbox to run in, and your code is executed. The code runs, returns a response, and then it's either frozen and reused for the next request, or it's terminated. You don't know which, and you shouldn't care which. Okay, so that's the compute part of a serverless story. But if we had a serverless compute story and no, but our database still ran on servers, this is where the RDS thing gets kind of challenging. Now you've got this cool, scalable, flexible ingest and compute capacity, but you've still got a database that has scaling challenges. Right? Because scaling any kind of traditional databases is, no matter how good or bad the database is, it's hard. So there's a bunch of other Amazon services that are also serverless, that also have the same attributes we're looking for with regard to scaling and being sort of automatically managed for us. And I'm going to divide these up into 3 categories. That first category, called abstract services, are the ones where, hey, it's an endpoint, it's an API. We tell it to do something, that something happens. We're not aware of the compute, memory, or disk behind that API. The second level is container services. I don't mean, in this case, I don't mean Docker, I mean where Amazon took care of the sort of platform for us. So RDS is a great example here, where it takes care of scaling, or it takes care of high availability and DR and backups and managing the database for you, but you're aware of the number of instances that you have, and the compute power they have, and the memory that they have, and the disk that they have. So it's one level less abstracted. And the bottom one, infrastructure services, these are ones that are essentially just VMs. You have to do everything, OS, application, the whole thing. So for a serverless application, we really like to just have abstract services, but you'll often have to dip down to the container services. You can almost always get away with not having any infrastructure services in a sort of modern day app. So here are the abstract services. This is not all of them, but this is a pretty good sampling of them. So IoT's on here, Dynamo Db's on here, Lambda's on here. Right, those are the ones we've been talking about. Those are completely abstracted, meaning, yes?
Would Amazon SageMaker be considered an abstract service, or would that be a...
Kind of. So when you launch a SageMaker or a notebook, you do pick an instance size. So I would say it's actually the next level down.
Okay.
One of the key things here is none of these things require to pick an instance size.
Yeah, you should probably know that network services is part of it, because most young companies don't have the expertise to manage instances. So network services might be really important to people to utilize.
Yeah, I mean, so the thing about all these services is you don't really worry about the networking component at all, right? These are literally public API endpoints. You make API calls, you don't even know what's happening behind the scenes. The next level down, you're a little more aware. So here, you do have to think about networking a little bit. You do have to think about compute capacity and scaling. It's easy scaling, it's push button scaling, but you're still thinking about how many instances, and how much CPU, and how much memory, and how much disk. So the canonical example here is RDS, which is Amazon's managed database product. So it wraps MySQL, SQL Server, Oracle, Postgres, MariaDB, and it runs those for you. They're still running on servers. You can see those servers. You know what those servers are, but you don't have to manage the OS and the application level. It's managed for you. And then the lowest level is the infrastructure services. So this is the ones where, look, it's just virtual machines essentially, or it's just a container. You're very well aware of the OS. You have to maintain the OS. You have to maintain the application software. You have to kind of consider HA and DR yourself in this layer. Okay. Good. Okay. So we're going to talk about a customer now named FratChem. They are a subsidiary of Koch Industries, based in Louisiana, with operations obviously in Texas as well. They make chemicals for hydraulic fracturing, and those chemicals are obviously liquid chemicals, which is how you do fracturing. But shipping liquid chemicals is challenging. You need specialized containers. When you spill them on the highway, people get really upset. It's a costly thing, and they're not very dense from a chemical point of view, right? Like, they're mostly water. So. And so it'd be really great if we could ship dry powder and hydrate that at the oil field, so that we're not shipping a bunch of water around.
Kind of like Tang.
Yes, exactly like Tang. Right.
This stuff's better for you.
I don't know. I think
Astron.
I drink the Tang before I drink the factory. So, but if you were trying to fracture with dry powder, it's a little bit of a square hole, round padding kind of problem, right? Like you need a liquid chemical to do fracturing. And so, this is not the actual device, but a device that looks like that. It's on a trailer. Is used to hydrate the chemicals. It's got a bunch of mixing chambers and heaters and whatever's needed to get that powder mixed with water and back into liquid form, right? But it's a huge piece of capital equipment. It's expensive, it's complicated, and it's our customer is providing it to the oil field as a part of the service. So if you do that, you really want to know, first of all, where is the thing in case it drives off on you. But more importantly, are we getting good chemicals out? Because the oil field companies, they don't really care that this machine exists. What they want is chemicals that they order. And so our customer has to ensure that the machine produces the right output. And to do that, it has to be getting good water. Is the water the right pH and the right temperature? Is the engine speed the right speed? Are there other indicators of failure on the horizon? Right? Because even a few minutes of downtime in these applications is super detrimental. So we instrumented it. That's not a real picture either, but I'll show you some real pictures. And we sent it to AWS. And we used just about every service I've been talking about in doing this. And we did it in 4 weeks. And so this is where customers are afraid of that integration work that it takes. We keep trying to tell people, hey, look, it's not that bad. It's very achievable. Okay, so anyone that's ever worked on hardware knows this is how this stuff starts. And if someone tells you otherwise, they're lying. This is always how it starts. Right, board and some wires. This is the first week of the project. A few days, and so when we took these pictures, we weren't taking them for the purpose of making a presentation, so they're a little messy. Second week, we started mounting on this piece of MDF. The piece of MDF that it's mounted on was made to slide into a spot that was sort of in the cab of that device. So like we had a spot carved out for us. And here we've got a DC to DC UPS. We've got some power control circuitry. That's that breadboard you saw earlier. Underneath that breadboard is actually a Raspberry Pi, which is not normally what we'd use in a production product, but we only had 4 weeks, and so it was fine. Now you've got some batteries here, because this device, when you turn it off, it's like a truck. When you turn it off, it's off. There's no residual power available to us. But we didn't want to just go offline as soon as the power was gone. We've got some batteries here to help us stay alive for a while. And this is a Hughes Inmarsat controller, just super cool. So when we're out in the middle of nowhere, with no cell connectivity, we can still communicate over satellite. This thing is self-aiming, so it's mounted to the roof of the cab, and you park the truck, and the antenna spins and finds the satellite and locks up. It's really cool. It was fun to test in our office. We had this satellite dish in the office trying to kill people. Because the thing just spins, man. You gotta watch out. And then we have a cradle point here, which we added for cellular connectivity. Again, in a more production-oriented design, we would have taken those components and just put them on our board and built a custom PCB. But in 4 weeks, it was easier to assemble some components. So this is just about the final design. I don't have a final design picture, but the only thing that changed after this was we cleaned up these cables, just tidied up the cabling. This is a web UI for it. So where are the tanks? What's their, or where are the devices? What's their status? We can graph multiple metrics from one or different metrics from different units over on top of each other. You can see we've got some in Texas. So the connectivity options then were actually pretty numerous on this device. If we had Wi-Fi in the oil field, which normally isn't the case, we can use it. If we don't have Wi-Fi and we have cell, which is about 80% of the time, we use cell. We have 2 SIM cards, one from AT&T and one from Verizon, and we'll just switch. If we don't have that, then we'll go to satellite. The problem with satellite is it's infinitely more expensive. I mean, like I can't exaggerate the numbers. It's $10 a meg or something, maybe more. And so when we're on satellite, we slow down our data rate. We transmit less frequently. We try to save data costs. But on the other 2, we transmit as soon as we can. And this is about a 1 second pulling interval request. The cloud side is totally serverless. It used all those services I talked about. So it's built primarily on Lambda, uses Kinesis, it does use Redshift, which is a data warehousing product that I didn't talk about. Uses Cognito and API gateway. Everything that you've kind of seen, this is assembled in that fashion. So the end result of that is that there are no servers to manage. Running this application after development is almost no effort. It just kind of self-manages. And we went from sort of an idea, literally a phone call saying, hey, we should do this thing, this is kind of cool, to a completed prototype in 4 weeks. And now we're working on how to harden that for the future, how to make this into a more production quality product. But a pretty cool example of ideation all the way through to a working product. And so I'll leave you 8 minutes early with this. This is actually last year. There were 6.4 billion connected devices last year, which was up 30% from 2015. And it's going to be 20.8 billion by 2020. And so when I talk to customers about IoT, the takeaway I'd like everyone to have is it's not if your industry will adopt IoT, it's whether you'll be the company that does it. I think there's no question that just about everything in our lives will be connected. So this is the time. I think 2018 is probably the start of this huge explosion going from 6.4 to 20.8. Questions?
Yeah, how long does it take that Lambda to spin up a new instance? Millisecond or?
Yeah, so it's pretty fast. It depends on your code too, assuming you have no startup code. So when you write for Lambda, you design it in a way to minimize startup code. Assuming your code's not the problem. It takes Lambda tens of milliseconds to launch a new container.
Okay.
And as if your traffic volume supports it, it'll instead of terminating them, it'll freeze them. And so you'll get reuse of containers, which will be even faster. And the runtime matters here too. So like the Java runtime is a bit slower than the Node one. So which runtime you pick matters.
I am assuming it's possible to feed real-time data from the sensors to your Amazon SageMaker, your machine learning platform, if you want to.
Yeah, through the IoT service, that's correct. Yeah, so you would ingest with IoT and then deliver to the SageMaker's
in real time as the data is
yeah, I would call it near real time.
How about the edge scenario? You did not put any edge in. It means that you can do store and forward, but it can do control command, a whole bunch of swarm of IoTs.
Yeah, so the applications I've worked on over the last 2 years, the #1 priority has been to reduce the cost of the end device. So if your goal is to reduce the cost of the end device, you're not going to put enough compute on it to do anything interesting. But if you do go, like, the threshold really is can your device run Linux or not. So if it's lower power than that, you're not probably going to do any analytics.
Let me ask you, if you have used a NK IoT, which is just a sensor and then send command kind of a thing, you that use your Raspberry Pi as your edge, with all the compute store and other capabilities, you would reduce the total cost of thousands. Well,
You're right. So if you're going to do Raspberry Pi or something at that scale, you definitely can do compute on the edge, right? Greengrass has a bunch of options for this. Amazon announced at reInvent that they're going to be able to push these AI models from SageMaker into the edge and do the predictions on the edge. But I would say using a Raspberry Pi is the exception, not the rule. Most of the devices that we're using are low-power microcontrollers that are like $2.
microcontroller is only the final node, but your Raspberry Pi is your edge node.
what I'm telling you is we build a lot of devices that don't have that. They are just microcontrollers. No other nodes.
Yeah, you mentioned cellular coverage in the oil patch. It kind of runs out of gas at about 80%. So that 20%, and I understand the expense of satellite. Have you looked at low power wide area networking choices like LoRa, Sigfox,
Yeah, so
other LP-WAN solutions, and put maybe a private network that could cover some pretty large swaths?
yeah, so we thought about it. In this case, with the POC level product, our customer wasn't prepared to invest in building a LoRa network, and there weren't LoRa networks just available. But there still really aren't. I guess we're building some now. And then Sigfox coverage is pretty weak. I mean, unless you're in a very populated area, there is no Sigfox coverage.
Right.
Which that's CBRS.
I mean, Sigfox coverage is far worse than cell coverage, I'd say.
So just to follow up, do you have a data point of what you think it costs to put up a LoRa type, an LP-WAN tower coverage area? Let's say you have a high point already, you've got a radio tower or a grain elevator or something.
I mean, the gateways are cheap. The gateways and antennas are cheap. They're hundreds of dollars. They're not. There's not really very much expense. The bigger expense is getting the towers put up and whatever permitting is needed if there's any permitting needed and all that stuff.
Agreed.
Sorry. Yes.
Yeah, in that prototype, you provide the options of Wi-Fi, cell, and satellite. Is that automatic, or do you have to have someone educated on that truck and the technology and the analysis of it?
No. In this case, we expected that people working this thing were going to drive it and walk away. And so it's all automatic.
So they are.
Yeah. So obviously it depends on your use case, but generally minimal human interaction is the way to go.
So it automatically
automatically
finds.
switch, yep.
It'll look for the lowest
It's
cost.
always looking for all of them and connecting to all of them, but it's picking which one to transmit on based on which one's the cheapest one that's available.
So near future with the CBRS, it'll probably be possible for like Verizon and AT&T to do like a quick custom site. Yeah. So I see that probably in the near future.
Yeah. And I mean, I do think the winner in connectivity in populated areas is going to be LTE-M. It's going to be what happens in these kind of oil patchy areas where there's not the incentive to build out the LTE network.
There's my card, we'll build you a LoRa network.
Perfect. Anyone else? There were some other.
What kind of latency you have with the huge network and the whole thing between the mode which is sending in information and the rate which you...
You're talking about specifically on satellite or?
That is satellite.
I mean, satellite's probably measured in seconds. Cell is in milliseconds.
I think the use case is about Toyota doing the automated connected cars.
Yep.
Connected cars. So what they're saying is the cost of sending data because of tremendous amount of data right from the car. So they're still trying to figure out, who to the provider for sending all the data.
Yeah, so connected car to me is an example of, so in a connected car, putting in enough processing power to be able to do edge compute is pretty simple, right? So when you move into the world of devices that have that kind of battery power, that kind of cost, it's pretty straightforward to say you would do a lot of edge compute and minimize your transmission as much as you could. Although again, when you minimize transmission, don't forget what you lose is that good training model. So you've got to think about transmitting enough good data that's not just the exceptions, otherwise you're not going to be able to refine your AI models at all. But you could do really interesting things like have 10% of the cars transmit all the data, and have 90% of the cars transmit only the exceptions. That'd probably give you enough training data to do useful things, and you can do edge compute. And Greengrass, Amazon's Greengrass product has a bunch of stuff in this space. I'll kind of finish that off by saying, there's no doubt in my mind for connected cars, you're going to go LTE-M, or LTE or LTE-M. You're not going to go LoRaWAN for connected cars. It doesn't make any sense.
No, but how about compressing the data?
Compressing?
Using data compression.
Yeah.
Where lossless data compression, that's the best way to reduce the size of the packet and do it the same way.
Sure, you can, I mean, look, we can compress the data, we can transmit less often, we can aggregate it, there's a lot of options. It's a matter of fitting to the use case.
I'm just curious, did you do any estimates on total AWS cost per month on that sample? Because you're only talking about, I guess, a couple
it's like
dozen.
$55 or something like that.
Yeah.
It's like trivia, lots
Or
of
how
noise.
many trucks can you?
So right now there's only 2 POC units out there, so it's not significant volume, but it doesn't matter. It scales really well because there's almost nothing that's running all the time.
I'm gonna thank you for putting a focus on the battery thing. I noticed it was the second largest bubble on your network diagram, and it's something you've made a very good point about using. So my question is, do you believe that LTE-M will satisfy the super low power, long-lasting battery package problem that is apparently satisfied by some LoRa solutions and certainly the Sigfox solutions, other weightless LP-WAN, the one I work with, N-Wave, where we can have years of coverage from, you know.
No, I don't think we're going to get to LoRa. So I'm most familiar of those options. I'm most familiar with LoRa. I don't think we're going to get to LoRa power utilization on LTE-M. The chips are still really new. In fact, they're really hard to get today. Like we struggle to even get enough sample units from the LTE-M chip manufacturers.
Yeah.
So it doesn't really exist yet. Like the network exists, but the devices don't. So it's hard for me to say, hey, we've tested it, and we think the power profile looks like this. There's some theories on it, and we're actively investigating it. But we're not far enough into this yet to say, here's the actual measurable power drop.
Yeah, I guess I'm asking a little bit about technology forecasting from you. You seem to have a good view of where this is headed. Will LTE-M cause people to say, eventually that power problem will be solved, and I don't need to put my money into the Sigfoxes, the LoRa's, the N-Waves, because I'm going to always have, you know, these corner cases where I need super long battery life in small form.
So Paul, from an LTE perspective, NB is much more of the solution
that's right.
than Cat-M1. So Cat-M1 has an architectural advantage over NB insofar as Cat-M1 has a really good profile for data in motion for transportation purposes, where NB is much more of a stationary and a smaller packet size. It's meant to compete more on the LP-WAN side than Cat-M1. But the problem with NB is nobody has NB yet. The first carrier that's announcing coming out with it is T-Mo. T-Mo said they're coming out at the end of the year. In reality, they might come out at the end of the year, but it's really 19 where you're going to see deployment. Verizon is committed to it. AT&T is Mets, and who knows about Sprint? Who cares?
Yeah, so I think that's a great summary. So Cat-M1 was easier for carriers to deploy, I think, because it's LTE based, right? They have it.
Same infrastructure, right?
Yeah, I don't know much about the infrastructure side of NB to know what they have to do, but when we get to NB IoT, I would hope we're going to see 50 or 60% of use cases where that power profile is good enough. I don't think it's going to replace LoRa in. So we've got some customers that are operating big office buildings, and they want to have sensors that are battery powered, so they don't have to run any cable in. They can just put the sensor on the wall and walk away, and they want 3 years of battery. Right. LoRa is going to make sense in that environment. Is LoRa going to make sense to build out huge networks that span huge areas? Yes. I mean, he says so. I think it's possible. But the cell carriers have such an advantage with their infrastructure. If, when NB comes out, it could be tough for those players. But we don't know the power profile yet. We just only know it in theory.
No, but just to answer your question, battery consumption is one of the key features in the standard itself. Right. When we talk Cat-M or Dynamo.
Yeah.
And there are features I can, discuss.
Wait, I mean, regular LTE, we know, is you're not going to get more than a couple days.
Well, so not to drag everybody off, but just quickly, size of package of cigarettes, 10 years, 10 miles, only need to send a bite 5 times a day. Right. But I got to go 10 miles for 10 years. Package of cigarettes, a box of cigarettes.
I don't think we're there yet.
No.
Okay, we're there.
Yeah, you might be there.
But it's not cheap. But it's coming down, and we're thinking, NB IoT, fine, LTE-M, fine.
Yeah,
it doesn't look like it ever gets there.
No, I don't think. Mine probably doesn't, and I don't think it's the same use case. Honestly, I think NB is low power, but not 10 years low power.
Yeah, we're talking about parking spot monitors.
Right.
Okay, guys, let's give Tolga a hand for his.